Hi, my name's Tim Decker. I'm here with
Jacob Begis.
Jacob's our optical engineer. We're both with Sierra-Olympia Technologies. We are here overlooking the Hood River Valley, and we have a Ventus HOT 900 midwave camera. We are here to do DRI testing. So we're looking at the ability of this camera to detect some objects far away based on DRI models that Jacob has made. Jacob, can you tell us about those DRI models?
Sure. So DRI stands for Detect, Recognize, and Identify. The DRI model will calculate and predict the probability of detection, recognition, or identification of the various objects in various conditions. So for example, you can model a vehicle, say it's a certain size and has a certain temperature delta from the background, and then you can put into the model that you have Ventus HOT 900, you put in the F number, the focal length, the pixel pitch, the noise equivalent temperature difference, and you can also model the atmospheric conditions. And all of that goes into telling you what are your chances of a human looking at a screen to detect, recognize, or identify that object in those conditions with that camera.
Would you say the weather this morning is favorable for this test?
I'd say the weather today is not ideal, but it could be a lot worse. You know, it's a clear day, there's a little bit of atmospheric scintillation, but it's not that bad, and there's a little bit of smoke, but again, it could be a lot worse.
So we've pre-selected some targets this morning, and we are right now have the Ventus HOT 900 pointed at a target that's about 10.5 kilometers away. So if you look into the distance, you can see a small canyon in the hillside, and there's a road that comes down that canyon. And there's a truck. We're going to try and detect, recognize, and identify the truck itself and a person in the truck, and see if we can find out what sort of objects that person's carrying.
We can see the truck, and it's pretty clear. You know, when you really look at it, that it is a pickup truck as opposed to a different type of vehicle. And I now see him walking out from the truck. You can see that it's a person walking. And we're also seeing right now there's a little bit of it would look like a jitter on the image, and that's from the scintillation through the atmosphere, which will randomly steer the line of sight at fast time scales.
Yeah, through 10 kilometers, there's quite a bit of atmosphere to look through. And actually today, we have a little bit of smoke accumulation in the valley, and that doesn't help us. But yeah, you can very clearly see a person walking around.
Now you guys see that that last walk back, there was sort of that blinking action.
Yeah.
So it looks like he might be holding a hot or reflective object.
That's
perhaps
catching glints from the sun. Yeah. Yeah, and actually the truck is helped a little bit by some reflection from the sun. You get specular reflection, very hot sunlight.
Yeah, because one major element of this is getting enough pixels on target, but the other element is having enough thermal contrast from the background. Because the truck is metal and in direct sunlight, it's going to heat up, making it easier to see at distance.
Jacob, do you think you can tell what he's grabbing there?
I cannot tell what he's grabbing. So far, I can't even tell he's holding something, but just now I get a glint of reflection, so...
You know that he's holding something.
Holding a man-made object,
yeah,
but not sure what it is.
It's really amazing because with the eye, you can't even see the road from here. So for this target, we are looking over the Columbia River, and there's a sandbar on the river, and our colleague Andy is down on the sandbar right now. He's got a small DJI Mavic Pro drone, UAV, and he's going to launch that Mavic Pro, and we're going to see if we can detect, recognize, or identify that vehicle. So we have a panning shot that's going to zoom all the way in.
And the drone is very tiny. So you know, a person is about 2 meters tall, but the drone's about 18 to 20 centimeters in its diagonal dimension. So it'll be a lot harder to see than a person at 10 kilometers.
And so we can see Andy walking away. There's, I think that the vehicle launch site is occluded by this tree, but we can clearly see Andy is walking away, and we're gonna see if we can tell when he launches the vehicle. Yeah, and you can make out his individual legs walking, so he doesn't just look like a blob that's floating on something.
Yeah,
you can tell it's a human walking.
We're getting some nice thermal contrast because he has the water behind him. Water is opaque in the infrared, so it's just going to look dark like you see in this image. You have the sandbar, which is a nice background temperature. It's pretty hot, so is our colleague Andy, but then the water will appear very cold because it's opaque.
Yeah, and you can see that sand on the sandbar has been soaking up sunlight and is re-emitting that energy right now. And so it's not too different of a temperature than that person, but yeah, indeed, the water this time of year, I think it's about 56 degrees Fahrenheit.
So when you're at the detect, sort of on the edge of the detect threshold for seeing an object, it definitely helps to have a cue of where you're looking. So in a lot of real world systems, for these long range applications, they might have a radar system or some other system to cue and say, you want to look in this area because you have an extremely narrow field of view. So how are you going to find a drone at 10 kilometers you know where to look for? You're never going to find it.
That's right. Because the field of view of the screen that we're looking for is, I think, less than a degree in horizontal direction.
I think we're just on the edge of recognize to identify for the person at 10 kilometers, so that's pretty good. And to be able to detect the drone at 10 kilometers, I think also aligns well.
When you set up those models, were you using probability thresholds at those distances?
Yes, that's a good point, Tim. The way the models operate or what's commonly advertised is the 50% probability of detect, recognize, or identify threshold. Meaning, if you had a human looking at a screen, in real life, 50% of the time they could correctly detect, recognize, or identify the target. So 50%, when you really think about it, is pretty difficult. So which is one of the reasons why these models can feel very optimistic.
Right. I can say my odds of recognizing Andy in the sandbar are better than a coin toss. So now we're looking at a target at the Hood River Airport, and that's about roughly 6 kilometers away. And we have Scott parked down there at the ramp. He's going to get out of his vehicle, and we are going to see if we can detect, recognize, and identify Scott.
Yeah, and in comparison to when Scott was driving and parking at 10 kilometers away, we should have a much easier time identifying the truck, and we should be able to identify Scott, meaning we should be able to get some sort of resolution to what he's holding and what he's actually doing besides just saying, oh yeah, that's a person.
So I can see Scott, that looks like a Toyota. That looks like a Toyota Tacoma. And I can see him walking around his truck, and it looks like he's going to get something out of the back. And it's interesting, you can see, I'm not sure if that's a reflection from the sunlight or if that's the engine bay that's warm, but there's a couple areas of his truck that are really a lot warmer than...
Yeah, a couple of hot spots, for sure. And you can really see where the hot spot is. You can really see that scintillation, where it just appears as though the hot spot is just jittering in place, not from the atmosphere.
So if the weather were a little different, if it were maybe cooler, we wouldn't see as much scintillation?
It depends on the sort of the thermal difference between the ground and the sky. So typically at the thermal inversion, early in the morning or near sunset, it will be lowest, but it's hard to predict.
We would be able to see Scott better if that wasn't there?
Yeah, because what the scintillation doing is it's basically introducing a blur. Because over the time frame where we're trying to look at and see what's happening, the line of sight is shaking, jittering about that point. So it's basically blurring the image. Only a little, but it definitely contributes.
It's almost like the imager is vibrating, but it's actually in the atmosphere.
Yeah, it's a similar result.
Yeah.
When I created this DRI model for the Ventus HOT 900, I took all of the specifications from the camera as built, and I also modeled a optimistic atmospheric and environmental conditions. We measured results, or in real life, we were able to detect, recognize, and identify targets in similar ranges to the model predicted. For example, the model predicted that for a 2-meter human target, that at about 9.5 kilometers you could recognize them. And I think we did just that with Scott at the 10-kilometer range, and also with Andy at the 10-kilometer range.
Thanks for joining us for episode 1 of our DRI testing series. We're going to be producing episode 2 on the Columbia River, viewing objects off of a boat. Like and subscribe on our YouTube page, and don't forget you can subscribe on LinkedIn as well and join in the conversation.